2x6s, most common right now. So it's a piece of 2x6, and then 16 inches or whatever later is another one, another one, another one. So what we have instead is in here, if you could look in there, we should have a truth windows facility. We have actually round wood. Instead of like big pieces like this, we actually have a round wood that's shaved off just on one little end, so that we can put any material we need. And then another one. So there's one here. So here there's one here and here, and then on the other side it's staggered. So basically that's the wall. That's the wall, and there's pure insulation in between. So no thermal. So that looking at the outdoor of the house, there's no thermal bridge that gets through. Whoops. Various things. So there's locations because of the fire where we had to use the pink fiberglass. There is all here is cellulose, which is a recycled newspaper treated with boric acid to be fire resistant. And you blow in. That's really actually easy to find almost anywhere these days. Not cherries or anything. Cellulose insulation. We also have this up here. You'll see this wall. It's called a light straw slip. So that is basically straw, and we have and mixed with a very light, like milkshake of mud and water, and then you mix it together, and that goes into place and forms. And then below this, we actually have some what's called slip and chip. So that's actually sawdust for a milling operation mixed with the same milkshake type thing. What I'm going to do is I'm going to talk a little bit about it, and then I'm going to do if you want to at some point just go in this closet and take a little look. So what there's a truth we call truth windows, where you leave a little bit exposed. With linseed oil, so it's a linseed and I think a little citronella solvent which helps it absorb into it. Solvents basically are something that allows something to be really less viscous, so it can actually absorb into something it normally wouldn't.
How often do you have to read?
This is, well, so it's a new thing, but it shouldn't. It's amazingly hard once the linseed salt. It should have to be redone. Yeah, maybe like whatever century, I don't know. Like it would get worn down. It's material be rebuilt forward. But no, I mean like so in Eugene, as you guys, I don't know if you guys know the place called Maitreya, but Rob was the first person I knew that built one of these. That was 15 years ago, and as far as I know, it's still doing great. He has lots of people living there. Yeah, so yeah. We're in transition from an outdoor kitchen, so definitely all our stoves are kind of sitting here on the side in somewhat dilapidation. But I can at least use them as tools to talk about. All right, so one thing Aprovecho as a stove, like Aprovecho, I mean, people heard the term rocket stove before. So yeah, so rocket stoves were born on this property. So this is the birthplace of the rocket stove. Yep.
They went all the way to Iowa.
Oh yeah, really? Okay. Yeah, so basically, I gave you guys a little history before of how the Lorena stove was first created, and then it turned out to be not that much of a success. Well, so what happened was Aprovecho went back in people in the 80s and really kind of went back to what we call first principles of design, and especially this guy Larry Winiarski showed up, and he basically had a doctorate in combustion, but mostly worked on jets and pulse jets and other cool things. But he found himself in a position in life where he really wanted to sink his teeth into something. So he showed up about, the story goes, at Aprovecho about the time that Aprovecho was also kind of hunkering down, looking at other things and going back to the drawing board with wood stoves. And he said, let's look at what you need for good stoves, and let's try to come up with something. Let's start with what we call principles of design. And so he said, well, let's look at the two sides of the coin. You know, basically wood does not burn. I don't know if you knew that or not. You cannot burn wood. So wood is this solid object, and you'll never be able to burn it, because what will happen is you will heat it to a certain temperature, and parts of that wood will turn into gas, and that gas will actually leave the wood, and then it can burn. Right, so that's going to come into importance. As it turns out, there's two important things for people like to use the term efficiency, and there's other ways that we really look at stoves, but people like having efficiency numbers of what's efficiency. So what is an efficiency? So efficiency normally is when people will be cooking a pot of food, and it's how much energy that's in your fuel you're using gets into that pot. And so we do a test we call the water boiling test, and the water boiling test is basically a simulated cooking test. We take in any stove, at the lab especially, people send us stoves from all over the world, and we'll test their stove. We're doing this thing called a water boiling test. And people are welcome to huddle with me, because I'm going to huddle because I got no rain jacket. So people can, if you don't have rain gear or you're wanting to, you can get closer to me here. So we do what's called a water boiling test, which is a simulated cooking test, basically taking a set amount of water and bringing that water up to a boil, and 5 liters is the amount that we've chosen. And working with a global group of people trying to devise agreed upon protocols for testing, so everyone's testing the same way. So right now the protocol is to bring 5 liters of water up to a boil, simmer it for 45 minutes, and see how much fuel you used. And at the end, you can get lots of neat numbers. You can get the time to boil, you get a high power thermal efficiency, which is the amount of energy that got in that pot. You get a low power thermal efficiency because you're going to simmer for 45 minutes. So if a stove's able to turn down from, from 1 and go up to 11, then it's a lot of difference. If a stove can only go at the really high power, then it's not going to do the same when you're in that simmer phase. So the idea of that thing called the water boiling test, bringing water up to boil, simmer 45 minutes, boil when the stove is cold, and then doing it again when it's hot. The idea is that's supposed to simulate all the environments that stove really will be used in the real world in a very controlled, replicable test. That's a water boiling test. So the reason why I said that is because one of the numbers that comes out of the water boiling test is a thermal efficiency of how much energy gets in this wood gets into the pot. So if you cook on a 3-stone fire, which we call 3-stone fire, traditional 3 stones with a pot on top. As it turns out, it really varies depending on how people use their fire. So if people really are lacking in fuel wood and are really maintaining it really well, they might get 20% of that energy into the pot. But if they're not doing very well at all, and like I was just in Paraguay a few weeks ago working with the Peace Corps, and there people have tons of wood in their mine because lots of illegal deforestation going on, tons of wood everywhere for them to use. So people really didn't care. It's one of the places I've seen least where people really kind of cared about the use of their fuel wood. Hope that's not on tape. I don't want to insult Paraguay. Sorry. Just don't put that on the internet or cut out that I insulted Paraguay. They're really nice people. But in general, they just really didn't have a reason to worry about their fuel wood. So in that sense, you might end up with only 2 or 3% of that energy getting into the pot. All right. So this is what happened with Aprovecho and the Lorena stove. Basically, they built this big earthen stove, and once they tested it, it turns out only about 6% of the energy got into that pot that was on that stove when it was cooking with one pot. So all of a sudden, if you're using a really well-tended 3-stone fire, you could be using 1/3 of the energy to get to than this Lorena improved stove. All right, so that's what happened. And so anyway, Aprovecho went back and said, all right, let's look at the principles of design. And the reality is there's 2 things going on. There's there's turning this into heat. All right, that's called combustion. Complete combustion is what you're going for. All right, but if you're trying to heat up this pot and you turn this into heat, great, you get 100% turned into heat. Your pot's over here. That doesn't do much for you. So the second part of the equation, besides turning this wood into heat, is doing what we call heat transfer. Transfer that heat into what you want. But similarly, if you don't turn this into heat and you just have a lot of smoke going off, that smoke is not energy, is wasted energy that can never go into that pot. So you can have high combustion efficiency, you can have high thermal heat transfer efficiencies, but you need both of them to get absolutely high efficiencies. All right. So first, Aprovecho said, okay, let's look at those 2 functions. And as it turns out, in combustion, you're trying to get really high temperatures. Well, in heat transfer, you're trying to get the heat to go into your pot, so you're basically sucking heat away. So those 2 things are fighting each other. So in permaculture, we talk about stacking functions. Well, in reality, you only want to stack functions when they don't fight each other. And so in a stove design, combustion and heat transfer are fighting each other. So what we do, the first thing we did was, or Larry did, was said, well, let's separate our functions. So when we look at all our rocket stove, and I'll talk about different designs, we'll notice that the place we're trying to heat and the place for combustion are in some way separated from each other. All right. So he started with, okay, so he said, so first let's look at combustion. And he said, what makes a cold? Let's start with the flame temperature. So when you burn a little yellow match, a little match, and has a little yellow flame, that's almost 2,000 degrees Fahrenheit, somewhere around 2,000 degrees Fahrenheit. All right. Well, what temperature does paper start to combust, or wood start to combust? Famous book. Ray Bradbury. 451 Fahrenheit 451. So that's where combustion will start to happen. And if you get up into the 1,000 degrees Fahrenheit, you're going to be getting really complete combustion pretty easily. So you have this yellow flame that is really hot, 2,000 degrees over, and you're only needing to get half that at the most. Why can you not? Because in every situation you have 4 things that are cooling your fire. All right. The first is wood. All right. Any wood that's coming in is ambient temperature. So in Celsius, that's around 25 degrees if it's room temperature, 75 for Fahrenheit. And so that is going to be cooling your fire that wants to be 400 to 1,000 degrees Fahrenheit. All right. The second is you have always have, whether it's 3 stones on the ground or whether it's a big 1,000 kilo Lorena stove, you have a massive stove body that is sucking heat away from your fire. So that stove body is going to be cooling your fire. The wood is cooling your fire, any excess wood that doesn't burn. This leads back to why I said wood only burns on the outside as the gases go out. So if you have a very large log, you have what is called a low volume to surface ratio. So basically you have a high volume to surface ratio. If you have a little stick, you have a very low volume to surface area ratio. So you have more area where combustion can happen, less cool wood where combustion cannot be happening. So small sticks. Anybody ever work with pellet stoves or use pellet stoves? They are metered little fuel. They're little tiny pellets, lots of surface area, little volume that are mechanically tossed into the fire. And that's the reason why if you look at a pellet stove flue gas, it's usually around 4 inches versus a wood stove one will be 6 to 8 inches. Because you can get so much better combustion with that metered little fuel. And a few other things happen in pellet stoves, but that metered fuel is one. All right, so we got wood. We got the mass of the stove. We have the air coming in. You need air for combustion, but a big open fire, 3-stone fire, can often have 20 times more cold air than is necessary for combustion. So all those 19 parts of air for every 1 part you need for combustion is cooling your fire because that air is coming in ambient temperature too, right? And the third thing is your pot. A pot of water will never be more than 100 degrees Celsius because as soon as it gets to 100 degrees, the water evaporates. That's a cooling process, keeping that water lower than 100 degrees. All right, so water will never be more than 100 degrees. So you have a fire wants to be around, a little over 1,000 Celsius, and it has a pot, it has sticks, it has air, and it has always has some type of body architecture of a stove, all 4 things. So what Larry said is let's look at what we can do in a simple design that can be repeated around the world to alleviate all 4 of those things. So what he came up with, and this is the one thing that Apro has really given to the world. So like all this stuff about combustion stuff, everybody else had known this and done this. The one thing that Apro did kind of give to the world is this thing we call a rocket elbow. All right? And that is an insulated combustion chamber that is sized for the task at hand. So eventually, once you know how you're building a stove, when I was first in the project in Central America building this Husa stove, we would figure out what size we needed for the griddle that was being used. It's a griddle stove. And so size of the task at hand. So I have worked with food dehydrators that have combustion chambers that are this big. I've worked with little camping stoves, little pocket rockets that are about this big. So it doesn't mean there's a right size or wrong size. It's just no bigger than you will need to have full of wood at high power for whatever task you have. So for this task, it's a pot that fits into this skirt. We'll talk about later.
Is that in relation to the height and the width?
Oh, so yeah, we'll get to the height. Yeah, no, it's so basically like you're gonna stick an amount of wood in here. You cannot get more wood than is in this space. So how big that space should be would be depending on what your task is. Meaning when I've worked with food dehydrators that were 4-foot by 10-foot griddles, that combustion chamber for where the wood was loaded was this big. All right. So that's for the wood fuel. And then we always add a shelf, and ideally even a grate back here, a little place with air holes. And what that does is a couple things. That is, it works as a carburetor. So remember I said, so the fuel was one thing. So I'll keep on fuel first. So not too much fuel, so you can't stick big logs in. The other is people just when they have a small combustion chamber, they're just led to cut up their sticks a little smaller. All right, they just do it. Just really kind of led to it. So a smaller combustion chamber makes people use smaller sticks. So that tends to be like the little pellets, metering the fuel. You also have a shelf sitting up there that is about 1/4 of the way up of the space is for air, the rest is for fuel. So a little space for air. Now what happens is when sticks are in here, the air has to go through here. It's one, limited, so it's carbureted. It's also preheated before it gets to the sticks. And it only really burns at the tips, so you get metered air, metered fuel. All right? Third thing was the stove body. So anywhere there is hot gases going, we insulate. So I will wish I had with me, I don't. Oh, here's a little piece. All right, so this is a refractory, insulative refractory brick. So if people want to pass this around, this is vermiculite and clay, and that has a density of about 1/3 to 1/4 what this normal clay brick might have.
Is that soft fiber?
This is just normal.
Soft fiber?
That is actually bricks we made. It's fired to cone 6, 1060, 1060 Celsius. So it's a vermiculite and clay mixture that we work with. Really easy, and we work mostly in places where it was sawdust and clay. But same idea. So what is insulation? Insulation is actually little pockets of air separated from other pockets of air. So this is what happened with Aprovecho in the big days with Lorena, is that people were cooking on this big, massive 1,000-kilo stove, and at the end of 6 hours of cooking, the outside of the stove body wasn't hot. So people said, aha, insulative. Look at that's insulating. And so, but people got mixed up between mass and insulation. So they thought because the heat, they weren't sensing that heat out there, that stove was actually insulating. But what it was doing was it was absorbing heat. So actually, when I crunch numbers and I look at that Lorena 1,000-kilo Lorena stove, and I look at how much energy it takes to raise that body up, I think 100 C is what I look at, which is doable in a cooking task. It's like 7 kilograms of wood just heating up that thermal mass, absorbed into that thermal mass. And most families, when we do water boiling tests and simulated cooking tasks, they can cook a meal in about 1 kilo of wood. So if you have this large 1,000-kilo body of stove and you're taking 7 kilos just to heat up that body, you're all of a sudden, you could have been using 1 in a very efficient stove versus 7 just to heat the body up. All right, but tangenting back. So anywhere there is heat, which is the combustion chamber or along the flow path of the gases, anywhere there's heat, we insulate. All right, so for combustion, we use insulative bricks like that. Sometimes we'll use non-insulative bricks that are thinner, backed up by sawdust, by ash or pumice or vermiculite. So, but anyway, the main idea is that the stove body itself, like I'll go look at a Husa stove over there, can be hundreds of pounds or thousands of pounds, as long as between it and the fire there's an insulative layer. All right, so the fire itself is not being cooled by that mass of the stove. It's not being cooled by excess air. It's not being cooled by super large sticks. It is also the pot. There's an elevation here. So we call it an elbow because the combustion chamber's here, and then there's some distance from the combustion itself until the pot sits. So the pot doesn't just sit right on top of the fire, which would be good for fuel use, but for combustion, it's cooling those flames. And so we have a distance from here to where the pot sits that is usually if this distance is X, this distance here is 1.5 to 2x. That's just our rule of thumb. A rule of thumb is something that's not true but works anyway. And so that's our rule of thumb is this. So if this right here is 10 centimeters, then this distance should be 15 to 20 centimeters before the pot. So this is a little lower than it should be, but it was just built for not being so tall. And so but for ideal combustion. So that's some combustion. So now you all know more than almost anybody out there building stoves on combustion theory. Congratulations. Give yourselves a hand. Around the pot, so the pot sinks down in here, and now the gases have to go around the sides of the pot. The space here is very small. How small? It's going to be, if we put a pot in here, and I wish I had the pot sitting around, but I do not. It's going to be such that the cross-sectional area, this gets a little bit, get your key together. The cross-sectional area the gases have to go through are the same throughout the stove. So at this, if you take a slice in time, the gases are coming through, and you take a slice in time, they have a square going through this combustion chamber that is about 100 square centimeters. All right? Well, now all of a sudden, a few seconds later, those same gases are coming up around the edge of this pot in a space between. So we want to have that cross-sectional area, that gap, which is basically the diameter of this circle minus the diameter of the pot that's displacing the gases, to be the same as it was in the combustion chamber. That's probably the hardest thing for most people to wrap their brain around, is the idea of constant cross-sectional area throughout the gases. So when we look at the Husa stove, it'll make a little more. It'll make a little more
What's
sense.
the advantage? What does that
Okay, so what does that do? What that does is that forces the gases to get as close as possible to the thing you're trying to heat without diminishing the combustion. So we say keep cross-sectional area the same. It's just a rule of thumb. It's not true. What you really want to do in any stove you're playing with, if you have the time and the desire to do it, is you want to keep reducing that gap to force the gases as close as they can to the thing you're heating. So in other words, you want this gas to be really tight if you could, but eventually, as you do that, oh, I should have brought my shirt. That's a cool diagram. But the firepower potential goes down. So as you reduce that gap, you're not allowing as much air to come in, and your fire potential power goes down. Your efficiency always go up, but if you're trying to heat a pot up, you might get super high efficiencies eventually, but you're not going to be doing the job you need to do, which is to heat up the water, heat up the food. So the rule of thumb that we have that just works well is just to whatever your cross section for the firepower you need to do your job. When you get in the heat transfer place, make it small and make it the same cross sectional area. Start with there and see how it works. And that's just a good rule of thumb. So anyway, so all this. So I mean, so if you go to our lab website, I mean, we have bread ovens, we have all kinds of designs that they just follow these same principles. Simple combustion chambers, and then wherever, look at where you're trying to heat and make the gases go around as much surface area you can in a gap that is sized so that as the gases move through the stove, they have the same cross section before as they did after, and then insulate wherever there's losses. So this is insulative brick. This isn't just earth and high mass earth and brick. This is that same insulative brick is all around this circle.
You know, in Central and South America, they cook on tamales a lot. So.
Yep. So this is my Husta stove, and for a griddle. So this is an example of a later version, but this was the Husta stove, the stove I designed, and it's the same idea. And we'll go look at the body of it and see how it was made to follow those principles. Nancy Hughes, she's in Eugene with Stove Team International, a great organization. They have with a circular kamal. Very simple stove, but same idea. It's basically this, but instead of this for a pot, it goes out into a kamal with that exact same space. So the space gets smaller and smaller as it goes out, because as you go out, you have more of a perimeter, so your gap can be smaller and have the same cross-sectional area. So you imagine the gases, they come up that hit the bottom. If you're talking about a kamal, at first they need a space this big, but as they get out here, they need a smaller space because they have a bigger circle.
Are all your designs like open source and on the internet?
Yeah. Yep. I mean, how well documented is the better question, but sure, yeah. But our designs are definitely open source. And so if you go to the Aprovecho.org, which is the lab's website, we have tons of free literature.
So the kamal, is it something that you purchased from her?
Yeah. So where she works, there's usually pretty standard circular kamals. And maybe, I actually don't know, maybe she does sell them with the stove to make sure that they like the quality's good. They won't.
Because that's a source of income for a lot of people in Central, at least in Central America. Making kamals.
Oh, you mean ceramic kamals?
Yeah.
Yes, ceramic kamals, my nemesis. Yeah, unfortunately, ceramic, same with pots, they're not very good heat transfer. It is a source of income, but so is illegal firewood harvesting. So yeah, it's a tough one. I mean, this is a little story. My first project that I was the Husta stove in Suyapa, a little place outside of Tegucigalpa, Honduras. After we were there about a little over a year, the firewood people that were selling firewood came up and were all angry at our project. And it's like, oh yeah, sorry, you gotta hurt somebody.
Yeah, well, look at it. They've denuded so much of their.
Totally, yeah. But these guys were like, hey, it's my family's business, I'm sure they were getting illegal firewood, but anyway, it was just interesting to face that. Like,
it's complicated.
Yep, life is complicated. But I was still happy with the choice to use less firewood. Yep. Well, we're gonna look at the middle stove over here. Yeah?
Pretty cool, huh?
You want to build here?
Yeah.
You can't build on fill. If you want to be level, you can build it up.
Okay.
Oh, so you would actually have like a multi-structure thing, or you dug it out. I don't think that was the reason. Yep.
Yeah.
Okay.
This is awesome.
Yeah, they're cute buildings, huh?
That is awesome. Wow.
If you can build something yourself, then that's the cost, I guess. But yeah, I think when he's pricing it out right now, he's saying that.
How much? Who's this for?
It'll probably be like for guest lectures and stuff, like just a place to put people up. Yeah.
Alright, yeah.
And hopefully eventually we'll have lots of them. So.